Amidst the chaos of swirling galaxies and exploding stars lies a silent, unseen order, an intricate pattern woven into the very fabric of the universe. What if the chaos that gives birth to galaxies isn't random at all, but a delicate dance of hidden laws shaping the cosmos from the shadows? Today, we'll explore how the underlying patterns behind cosmic chaos reveal a profound unity, transforming our understanding of the universe's most mysterious phenomena. Get ready to see the chaos in a whole new light, because within every burst of disorder, there's a blueprint waiting to be uncovered. Understanding chaos and order in the universe. The universe is a vast mosaic of seemingly unpredictable phenomena intertwining with underlying patterns that defy simple classification. At first glance, chaos appears to dominate cosmic processes, stars spiraling unpredictably, galaxies colliding in complex dances, and regions of space where gravity's influence seems random. Yet, beneath this apparent disorder, scientists have discovered that chaos often operates within a framework of deep-seated order. Fractals, for instance, exemplify how complex, self-similar structures emerge from simple rules, mirroring the intricate patterns observed in celestial formations. The nebulae, with their swirling filaments and recursive structures, showcase this beautifully. These phenomena hint that the seeming randomness we observe is not entirely disconnected from an intrinsic structure that guides and shapes cosmic evolution. In physics, chaos theory has revolutionized how we understand the delicate balance between predictability and unpredictability in the universe. Small differences in initial conditions can lead to vastly divergent outcomes, a phenomenon known as sensitivity to initial conditions. Take the orbit of a planet in a multi-body system. While it follows gravitational laws, tiny variations in the system's starting state can cause long-term unpredictability. Yet, within this chaos, patterns still emerge. For example, the formation of spiral arms in galaxies and the clustering of galaxies into larger structures like superclusters suggest a hidden order driving the organization of matter over colossal scales. These patterns are evidence that chaos and order coexist, woven together into the very fabric of space-time. Mathematically, chaos and order are often examined through nonlinear equations that model cosmic phenomena. The solutions to these equations reveal stable attractors, states toward which systems tend to evolve, and strange attractors, which produce complex, fractal-like trajectories that never settle into a fixed point. Such mathematical insights show that what appears as disorder is sometimes a dynamic process following rules too complex for simple intuition. Space weathering processes on planetary surfaces, turbulent flows in astrophysical plasmas, and even the birth of stars from collapsing molecular clouds all demonstrate how chaos operates under constraints that subtly shape the universe's architecture. This interplay helps explain the balance of randomness and structure that defines the cosmos. Examples from observational astronomy continuously challenge the assumption that chaos equates to disorder. The observed regularity in the orbits within planetary systems, the repetitive patterns in cosmic microwave background radiation, and the galaxy distribution across large portions of the universe all suggest an underlying set of principles that modulate chaos. These principles are often rooted in fundamental physics, gravity, electromagnetism, quantum mechanics, serving as the rules that guide cosmic chaos along certain pathways. This recognition implies that what we consider chaotic may merely be a different scale or perspective of an elaborate order, one that reveals itself in the complexity rather than simplicity. Exploring this duality deepens our understanding of how galaxies form, evolve, and contribute to the grand order that unites the universe. The origins of cosmic chaos and its patterns. Chaos in the cosmos isn't just randomness. It's a complex tapestry woven from underlying laws and patterns that appear to be contradictory at first glance. The universe's initial conditions, extreme density, temperature fluctuations, quantum uncertainties, set the stage for a process that seems inherently unpredictable yet follows profound mathematical principles. The behavior of particles and waves in these primordial moments hints at deep connections between chaos and order, suggesting that the universe's most sprawling structures arise from fundamental laws operating at scales far smaller than we can directly observe. Astrophysicists often point to fractal patterns and self-organizing principles as evidence that chaos isn't purely disorder, but a form of patterned complexity. Galaxies themselves, while seemingly randomly distributed across the vastness of space, display filamentous structures and clusters that can be described using mathematical models rooted in chaos theory. For example, galaxy clusters form along cosmic filaments, vast, web-like structures that resemble fractals, where similar patterns repeat over different scales. These arrangements hint at a hidden order woven into the very fabric of the universe, originating from early quantum fluctuations that were amplified during inflation. The role of turbulence and gravitational instability in shaping cosmic features further emphasizes this interplay of chaos and structure. As matter clumps under gravity's influence, it creates regions of intense activity, such as star nurseries and supermassive black holes, all within a chaotic environment. Still, striking patterns emerge: spiral arms of galaxies, the distribution of dark matter, cosmic microwave background anisotropies, all bearing the imprint of initial chaotic states that were modulated and organized by natural laws. These phenomena suggest that chaos isn't simply randomness, but a stage upon which order is sculpted, revealing an intrinsic harmony within apparent disorder. Ultimately, the origins of cosmic chaos seem less about unpredictability and more about the universe's capacity to generate complexity from simple rules. Mathematical models like chaotic dynamical systems help explain how tiny variations in initial conditions can cascade into the vast diversity of structures we observe today. From the wobble of particles in quantum foam to the grand sweep of galaxy clusters, a pattern of underlying coherence underpins what looks like chaos. This hidden order fosters a universe in which complexity isn't an anomaly, but a natural consequence of the universe's self-organizing tendencies, an intricate dance between randomness and structure that continuously shapes the cosmos. Emergence of structure from chaotic processes. Within the seemingly endless dance of chaos, patterns often emerge that hint at an underlying order, suggesting that even the most turbulent systems are capable of giving rise to structure under specific conditions. This phenomenon is especially evident in the formation of galactic structures in the universe. Clouds of gas and dust, subjected to gravitational forces and various instabilities, do not simply disperse randomly. Instead, they give birth to galaxies, star clusters, and vast cosmic filaments. These structures are not preordained but evolve from complex, chaotic interactions, illustrating how randomness can seed order over time. Mathematically, the emergence of structure from chaos can often be described using principles from chaos theory and nonlinear dynamics. For instance, the concept of bifurcations shows how small shifts in initial conditions lead systems to develop entirely different behaviors. In astrophysics, this means minute variations in the density or velocity of cosmic matter can exponentially influence large-scale patterns. The process resembles how whirlpools form in turbulent water. Initially chaotic eddies organize into coherent vortices. In space, microscopic fluctuations in density within primordial gas clouds gradually amplify, influenced by gravity, resulting in the large-scale structures we observe today. These processes underscore that order can naturally arise from irregular, unpredictable systems through self-organization. A compelling example of emergence includes the formation of spiral arms in galaxies. Instead of being static arrangements, these arms are density waves, regions where matter tends to cluster temporarily, moving through the galaxy's disk like traffic jams on a highway. These structures are not fixed. They result from gravitational interactions and the collective behavior of countless stars and gas clouds. Over cosmic timescales, such patterns sustain themselves, appearing to be stable yet constantly evolving, demonstrating how transient chaos can generate persistent organization. This interplay between chaos and order highlights the universe's ability to impose structure through dynamic feedback mechanisms. Furthermore, the idea extends beyond astronomy into various natural systems. In ecosystems, chaotic fluctuations in population sizes can lead to stable cycles or pattern formations, such as lichens creating regular mosaics across rocks. In the realm of weather systems, seemingly unpredictable storms can still produce seasonal patterns or climatic zones. These examples reinforce that chaos, far from being purely destructive, acts as a fertile ground where order can develop, driven by interactions that, although initially random or chaotic, organize into meaningful, resilient structures. The universe's grandeur might lie in this very capacity, transforming raw chaos into the complex tapestry we observe, moment by moment. The invisible laws governing cosmic complexity. The universe's grandeur rests on an intricate framework of principles that operate beyond everyday perception, often referred to as the hidden order of chaos. These invisible laws shape everything from the formation of galaxies to the dance of subatomic particles, revealing that chaos is not merely random. Instead, it embodies a complex pattern driven by underlying mathematical and physical rules. For example, the structure of galactic clusters and the filamentous web of dark matter follow statistical distributions and gravitational dynamics that are deeply interconnected. These patterns emerge over cosmic timescales, illustrating that chaos and order are two sides of the same coin. This balance between randomness and predictable behavior is exemplified in the concept of fractals, a mathematical way of describing structures that are self-similar at different scales. Galaxies themselves exhibit fractal-like arrangements, meaning smaller systems resemble larger ones in form and organization, driven by gravitational interactions. Despite the apparent disorder, the process of galaxy formation adheres to the laws of physics, especially those governing fluid dynamics, thermodynamics, and gravity. The behavior of particles swirling in accretion disks or the clustering of stars within galaxies exemplifies how macro patterns independently emerge from microscopic chaos. The principles enabling such cosmic complexity rely heavily on concepts from chaos theory and nonlinear dynamics. These theories suggest that tiny variations at a fundamental level can produce vastly different large-scale structures, a phenomenon known as sensitive dependence on initial conditions. The cosmological structures we observe today are the results of myriad small fluctuations amplified over billions of years. Though unpredictable in specific details, the overall distribution and large-scale patterns follow probabilistic rules, governed by the statistical properties of initial quantum fluctuations and gravitational forces. This delicate interplay of order and chaos creates a universe that is at once unpredictable and comprehensively structured. Underlying it all is a set of subtle yet universal rules, laws that function invisibly like the gravity that holds planets in orbit or the electromagnetic forces enabling atoms to hold together. These laws are woven into the fabric of space-time and matter, with their influence extending through multiple scales. The cosmic web's filaments and voids owe their existence to the behavior of dark matter and primordial density fluctuations, obeying the same invisible principles that underlie chaos theory. In essence, what appears as chaos to the naked eye is governed by a deep coherence, an intricate order that shapes the vast, swirling complexity of the universe. Implications of chaos theory for galactic formation. Chaos theory reveals that the universe's earliest moments were marked by an intricate dance of unpredictability and subtle order. Small fluctuations in density and energy, seemingly random at the start, ultimately contain the seeds for the grand structures we observe today. Rather than conforming to straightforward, linear models, galaxy formation appears to follow nonlinear principles where tiny variations in initial conditions can lead to vastly different outcomes. This challenges traditional notions that cosmic evolution strictly follows predictable, smooth pathways, instead emphasizing a delicate balance between chaos and pattern. In practice, the implications of chaos extend deep into understanding the distribution of matter across the cosmos. Galaxies emerge not solely from uniform matter clumping together, but through a complex interplay of gravitational forces, quantum fluctuations, and dark matter interactions. These factors create a web-like cosmic structure called the cosmic web, composed of filaments, clusters, and voids. While the pattern looks organized at large scales, the underlying processes display a sensitive dependence on initial conditions, meaning tiny differences in early universe conditions could spawn entirely different galactic arrangements. This explains why some regions evolve into dense galaxy clusters while others remain vast empty spaces. Chaotic microvariations dictate large-scale architecture. Moreover, chaos theory adds a layer of understanding to the dynamic stability of galaxies over cosmic timescales. Instead of being static entities, galaxies are constantly influenced by minor interactions, gravitational tugs from passing objects, dark matter substructures, and internal dynamic instabilities that can amplify into significant morphological changes. These seemingly small disturbances can produce spiral arms, bars, or even trigger starburst events, illustrating how deterministic but unpredictable processes drive galactic evolution. This perspective also illuminates why predicting the exact future of a given galaxy remains so difficult. Small initial differences lead to divergent evolutionary paths, a hallmark of chaotic systems. Finally, the implications reach into the very fabric of cosmology. Recognizing that chaos underpins galactic formation fosters a nuanced appreciation of the universe's complexity. It highlights that order, in the grand scheme, may arise from fundamentally unstable and unpredictable processes. Instead of seeking perfect predictability, scientists acknowledge that the universe's beauty and diversity stem from a deep-rooted chaos operating within a framework of natural laws. This recognition deepens our understanding of cosmic origins and reminds us that apparent randomness often harbors an unexpected and elegant underlying pattern. As we've seen, the universe's chaos isn't random at all, but woven with an intricate, hidden order that gave rise to galaxies and the cosmos we observe today. From the fragile balance of cosmic forces to the fractal patterns underlying space itself, there's a profound elegance emerging from apparent disorder. It's a reminder that even in chaos, there's a story waiting to be uncovered, one that connects us to the very fabric of the universe. Thanks for exploring these ideas with me. First, hope you found them as fascinating as first did. If you're curious to dive deeper into the mysteries of the universe or explore more about the unseen structures shaping our reality, stay tuned. First V, you got some exciting topics coming up that will take us even further into the cosmic unknown. Until then, keep pondering the patterns in chaos. They might just hold the key to understanding everything.